Okay, I think we should go ahead and get started. So, good afternoon. I'm Dean Eccles. I'm one of the associate directors of IDSS, and really, it's our pleasure to have today's speaker, Aaron Clauset, who's somebody really working at the interface of network science, statistical physics, computer science. I think a lot of people probably know him for telling a bunch of statistical physicists that there were better ways of testing some of their models of networks and whether they really were power laws. But I think a lot of his work over the last decade has been focused on science of science and sociology of science and issues of kind of inequality and the structure of, say, networks of hiring, how maybe all we do here is hire people from Stanford and all they do is hire people from MIT, and interventions that might improve kind of the state of information diversity and representation in science. So anyway, I think he's going to talk a little bit more about some of this science of science aspect. And so really, it's our pleasure. Let's welcome Aaron.
Thanks, Dean. It's a great pleasure to be here. This is my first time visiting IDSS, which has been on my radar since it was created many, many years ago, and is filled with wonderful people who do interesting things. So it's really fun to be here to be able to talk about one particular project and a few additional follow-ups or related things we did, thinking about how networks are related to productivity and prominence in scientists and how networks offer us a way of understanding some of these puzzles that have been observed for many, many years in trying to understand where differences between scientists come from in these respects. Before that, because this is a networks talk, I wanted to make a plug for some network stuff that I also do. I'm writing a textbook called Network Data Science. This might be the final cover, I don't know. And it's meant to be sort of an introductory graduate text or maybe upper division undergraduate text that teaches you how to use network data to do science. So you're really about asking and answering scientific questions about systems using network data. This book is based on a class that I teach at Colorado. The lecture notes are online if you're interested in network stuff at that URL. And then I also have this other resource that my group runs called the Index of Complex Networks. If you're ever looking for network data, either to run experiments on or to get some ideas about what people use networks for, this has about 600 different research quality data sets indexed in it. The data is stored elsewhere. This is just a way of sort of keeping track of things. It's a lot of social networks, perhaps unsurprisingly, but plenty of biological information and technological networks as well. Okay, so let's talk about science and scientists and networks. I want to convince you that networks are a key part of how science actually operates. My interest in the science of science, which is sort of a general interdisciplinary field trying to understand how discoveries get made, who makes discoveries, how the infrastructure of science sort of shapes what comes out of the scientific community. Networks are sort of the foundation of almost every activity we do in science. For instance, scientific training is a network because you collaborate with your advisor who has their own collaborators. And so that network of advising relationships, that's how information gets passed from one generation to another. Hiring is a network, which institutions hire the graduates from other institutions, as Dean was mentioning. I've written several papers on that. Collaboration networks, who publishes papers with each other. Teaching in terms of the interactions between the instructor and the students. There's networks there. Even the attention that we give different scientific results or papers is a network. Citations represent a network because one paper cites another. And so the bibliographies are sort of like attention tokens that we distribute in the system. And then, of course, Google Scholar and Semantic Scholar use that information to give you results. And so the attention network is actually driving what we even look at in terms of reading. Peer review is definitely a network in the sense of these interactions between reviewers and authors, et cetera. And so networks are the basis of science because science is a social endeavor. And so if we interact with each other in a scientific context, there's a network underneath there. But I'm going to argue today that networks are really an unequally distributed form of social capital. And that unequal distribution of that social capital has an impact on scientific careers and citations and publications and so on. And so if we want to understand this sort of general question that animates a lot of my work in this area, which is how does the composition and the structure of the scientific workforce influence what discoveries get made, then we really have to think about the networks and how they represent this sort of unevenly distributed social capital. To make that idea concrete, let me take a page out of my own history. When I was a PhD student, I started working with this very famous professor, Mark Newman. He was not my advisor, although some people think he was because we wrote several papers together. And this was the period of Mark Newman's career in which he was publishing like one paper a month, and 2/3 of them were solo authored papers. So like just an incredible volume of production at this time. Like I could barely keep up with digesting his papers. So he's very prominent and very productive. And I had the privilege of being able to work with him during my PhD. And so that collaborating with a productive collaborator made me look more productive too, because he writes so many papers. It was pretty easy for him to write a paper with me. The work he did made that paper go faster. And of course, his prominence also surely lifted my own prominence, because if people want to read a Mark Newman paper and I'm an author on that, then they're reading my paper as well. And so the argument here is that the productivity and prominence of your collaborators influences your own productivity and prominence, that we can't really decouple these two things. So if you look at my track record alone, you're seeing sort of the shadow of Mark Newman's track record on some of that work as well. So this is one of the questions we want to try to answer with this talk, which is how much does who you work with impact your own productivity and prominence? And to do this, we have to marginalize out the network effects, right? Because this network right here is a collaboration network among network scientists. There's Mark Newman. This is from 2006, so right after my PhD. And let's see, that's me right there, tiny little dot, right? And then there's some other familiar names, like there's Laszlo Barabasi. Who else might I pull out? My PhD advisor is Chris Moore, he's somewhere over here in the Mark Newman circle. So if this is your collaboration network and you want to understand the individual productivity and prominence of any one of these nodes, you have to account for the productivity and prominence of their neighbors, their collaborators. So we have to marginalize out that network structure in order to get the individual values for these things. Okay, so let me give you an example. We'll walk through how to do it. Here's another network, collaboration network, pulled out of our data. This is for Giorgio Parisi, who won the Nobel in Physics in 2021, nominally for complex systems type ideas, so it's kind of fun. He's the node right here, and you can see that he has a huge number of collaborators, right? So this is not just his first order neighbors, there are some second and third order neighbors in here too, so this is sort of like a punch of the network around him. But you can see that he has a huge influence over this part of the graph. So if we wanted to understand the productivity and prominence of any one of these nodes, we have to account for the fact that Giorgio is an incredibly productive individual and very prominent, especially after the Nobel Prize. Okay, so we want to estimate individual productivity net of the co-author's own individual productivity. So we're going to use this little worked example here of 3 nodes, and let me just throw some numbers on the page for us. So we get to observe the papers that get published. We're going to assume here that papers only ever have 2 authors on them. We're going to do that when we get to the data by just ignoring all middle authors. So we only have the first author and last author. That sort of cleans up a messiness with multi-author papers. Sorry to middle authors. I know, violence in science. So we're going to assume that it's just pairs of people. So every paper is just an edge. And so we have 3 pairs here. We have the red and the blue. That's this one right here. We have the red and the gold, which is this one, and then the blue and the gold, which is that one. And I'm just going to lay down a number of publications that represent them, and the thickness of the line is proportional to that number. And I'm also going to note like how many years those papers are published over. So you can see that this is a 3 and those are 2. So the rate here is not just 1 or 3 or 4. Okay. So the question is, who is individually the most productive? So let's do a quick poll. Which of the 3 people, red, blue, and gold, is the most productive individually, net of their co-authors, given this? So who thinks it's the red individual? Who thinks it's the blue individual? Gold individual? Okay, great. Consensus, it seems, that we think that the gold individual is the most productive, maybe because they have the thickest edges attached to them. Okay. So we want to make this more concrete, so we're going to write down a probabilistic generative model for the edge weights. So we're going to fix the graph in terms of who collaborates with whom, and we just want to know like how many collaborations are we going to observe? What's the weight on each edge that we expect to see between a pair of people? So here we're going to model the probability of observing nij, that's the edge weight, over some period tij, conditioned on these latent parameters, lambda I and lambda j, which are the individual productivities, your sort of latent individual amount of papers you can write. And we're just going to model this in the stupidest, simplest way possible. We're going to assume that productivity is additive. So if Dean and I work together, we're just going to add our lambdas together, and that's going to generate the mean of this distribution, the Poisson, that tells us how many papers we generate in a given time period. It has to be somewhat random because there's all these contingent factors that can slow down or speed up a project, like annoying editors at journals who demand that you run new experiments, or things like that. So this makes it really simple to do the estimation, but the network makes it more complicated. So I'm going to skip over some of the methodological details about how we estimate these parameters. I'll gesture at that in a minute when we talk about the data, but just think about this as our function. So now the question is, what does the estimate come out to be? If you work through the math for this little example, what you find is, correctly, you all guessed right that the gold individual is the most productive, but look at these two. Right? So the red individual here is more productive latently than the blue individual. But that's confusing because if I sum the edge weight of the blue individual, it's larger than the sum of the edge weights on the red. Why? Oh, it's because of the gold individual. The gold individual is lifting up both of their collaborators' productivity to some degree. And so when you marginalize that out, what you find is that you get more of a difference between the blue and the red. Okay. So the productivity one is relatively straightforward. Now let's ask a slightly different question, which is, how do we estimate individual prominence? So here we're going to define prominence not in terms of citations directly, because they have sort of complicated endogenous effects associated with them, but instead we're going to turn it into counting papers again, so that we have small integers, and we're just going to count the number of high-impact papers. And high-impact paper in the data analysis is going to be defined as publish a paper in a given year in a given topic, and that paper ends up in the top 8% of citations for that year. So we're still accounting for attention in the sense of how many citations papers get, but it's a relative measure. And so it's a small probability of whether or not any paper ends up in that top bracket for a given year, but at least we're controlling for the year, which accounts for non-stationary effects over time, and we're accounting for topic, which allows us to distinguish the fact that like papers in neural networks get a lot more citations than papers in political economy, for instance. So again, we're just going to count papers. Here's our example for this one. Same 3 people. Now we have the same number of papers, but we're going to define a high-impact paper as this hit paper, and we're just going to count them. So this 1 high-impact paper out of this pair, 1 out of this pair, and then 3 out of that pair. And the question is, with these numbers, who is the most prominent? Well, again, we need a generative model to generate these numbers. Same sort of form. Now we're going to have a different latent parameter, theta I and theta j, which is the individual prominence, the sort of likelihood of generating a paper that gets that amount of attention from your community. And we're just going to model it as a binomial, again, making sort of the simplest, dumbest assumption, which is that prominence is additive. We work through the math here, put up the estimates for the lambdas because I want to compare them. What you find is that the theta values give us a different story than the lambdas did. So in lambda, remember, the gold individual was the most productive, most papers, but under the prominence, we find that the blue individual was the most prominent. And so this is nice because if you look at these numbers, what you can find is that the red individual is sort of middle productivity, middle prominence. The blue is low productivity, right, smallest number, but the highest prominence. And then the gold individual is high productivity, but low prominence, right? They get almost a 0 here. And so this is nice because it shows us that we can have independence between these 2 different parameters, okay? So our model here is the simple Poisson model for the productivity and a simple binomial for whether or not papers become in this sort of hit category. So we're going to take this model now and apply it to large data to try to actually estimate these kinds of marginalized values for productivity and prominence. Here we're using the Microsoft Academic Graph, which is a large-scale bibliographic database. So this is just a huge pile of papers from many, many different fields. We're going to focus on STEM fields primarily because they have collaboration norms, right? So in economics, it's not as normal to have multi-author papers. And so you don't have a network then. If everybody writes solo papers, there's no edges. And so you couldn't use any of this machinery in a field like that. But with STEM fields, you have this problem, which is that you have these middle author, these papers that have many potential middle author papers. Like for instance, the LIGO paper had so many, this is the paper that discovered black holes collisions using gravitational waves. Absolutely cool paper. That paper has so many authors on it that they couldn't even put the affiliations in the paper. That had to be in a separate file, right? So it's like 2 pages of names and then 4 pages of science in that paper. And so that presents a real problem because if you look at the collaboration sort of footprint of who works with whom, if that paper has 100 authors on it, that's a clique of size 100, all with the same edge weights put on the graph. So because of the heterogeneity in number of authors in a given field, we're just going to drop the middle authors and just focus on the first and last, primarily because those are, in these particular fields, with some exceptions, theoretical computer science and some parts of math, those are the most important members of the team, right? They're the student or the junior member who led the effort, that's the first author, and they're the senior member who sort of designed the research, who's the last author. It's not perfect, and we can talk later if you want about how this might mess things up in terms of the estimation, but these are the fields we're going to look at, and we're just going to look at author pairs, which gives us this pairwise network. As I mentioned, we're going to define a high impact paper as one that is in the upper 8% for a given year and field. So this controls for time, and this controls for field heterogeneity. This number here, it's not that important. You can make it 10 or 15% or even 5%, and you get qualitatively similar results. This one gave us a network that had the right sort of density for mitigating some of the sort of nasty parts of the estimation. Like for instance, if you have a tree structure attached to the graph, then the estimation of the parameters becomes degenerate inside that tree. And so if you make this too high, then you have too many of those trees. So we have to lower it to some degree. Okay, so this is the data we're going to look at. We're going to estimate the individual parameters, lambda and theta, for every one of these scientists. Oh, I forgot to mention. We're going to focus on mid-career researchers, particularly because they have enough papers by which to estimate these parameters. If you looked at early career researchers, they often in some of these fields don't have enough publications to get good, robust estimates of their lambda and theta parameters. And some of the analyses we want to look at how the early career compares to the later career. So we're just going to focus on papers on researchers who have at least 15 years of publishing history. So 15 years between the first publication of the data set and their most recent one, and that have at least 10 papers. So this guarantees that we get enough data to make our estimates. Okay, so we're going to estimate our individual parameters. We're going to estimate them over time so we can see how these values wiggle from 1950 to today. We're going to use this bootstrap convex optimization in a supercomputer in order to estimate them. And then we're going to look at how these individual parameters now covary with other things, right? So the idea was to try to marginalize out the effect of the network. Once we've done that, we have these individual parameters. That's essentially more covariates at the individual level that we can ask, how do these things relate to other covariates about those individuals, like gender, for instance? Okay. So before we actually do any of the real analyses, we first want to check to make sure the model is giving us sensible results. We've made some pretty strong assumptions about the linearity of productivity and the linearity of prominence. We want to make sure that we're not getting stuff that just looks crazy. Here's the joint distribution of the two parameters. So the y-axis here is the latent prominence theta, and the x-axis is the latent productivity. I want to point out that these sort of marginals here are nice sanity checks. So the marginal distribution for individual productivity is nicely sort of Gaussian, with an average right here around 0.42 papers. So this estimate says that across these 6 fields, across these 200,000 mid-career researchers, the average number of papers that they could publish themselves per year with no help from their collaborators is 0.42, which honestly feels about right as a senior researcher. Writing a whole paper by myself every 2 years with teaching and administration and everything, okay, like this is close enough to pass the smell check. The individual prominence, however, is highly skewed, right? So most of the density is down here close to 0, meaning that the large majority of researchers have essentially 0 probability of publishing a paper in the top 8% of citations in a given field or in a given year. That also passes the smell test, because being in that upper division is really hard. And here we're talking about 200,000 researchers. So there's just not that many of those high impact hit paper tokens to distribute. So most people are going to be down here. But there are some individuals who are really good at this, who have a number of papers in that sort of upper echelon. So this also sort of feels like it's about right. You can also look at the correlation between these newly estimated parameters and other sort of raw statistics that we can get out of the data. So for instance, if I look at the correlation between how many papers I write and, for instance, having highly productive co-authors, I find a very significant correlation, right? So this is the Mark Newman effect, in which if you work with somebody who's incredibly productive, that tends to boost your paper count. And similarly, if I have a highly prominent co-author, then that also boosts my citation count. So we're seeing the kinds of effects in the data that we would expect, given the assumptions that we put into the models. Okay, so this seems like we've done a pretty good job of marginalizing out that network, and now we can look at these individual values. So let's turn now and try to solve one of these puzzles that's been sort of persistent in the literature. Over the past, well, 80 years, is that right? 60 years. So since the 1950s or so, essentially as soon as people started looking at publication counts and citation counts in science, they noticed that men and women publish at different rates. And every study since then has sort of found the same pattern, that men publish more papers than women. And there has been many, many papers written to try to explain why this is the case. It's also true that men receive more citations than women. And so the question is, well, why is that? Okay? So first, let's just check that in our data we do recover the same pattern that has been seen in the past 60 years. Indeed, we do. So here's publications by the 15th year of research as a function of time, and we see that the blue line, which is for men, is consistently above the red line, which is for women. So the gap there represents that productivity puzzle or productivity gap between men and women. And similarly for citations, you can see that men have more citations than women in their 15th year. And so if you just look at the raw numbers, you see this persistent gender difference. But if instead of plotting these raw statistics, we instead plot our marginalized versions, so we're going to net out the effect of the network, we find that they disappear. So here, this is the latent productivity in the 15th year, and you see that there's no difference between the men and women line. And for prominence, there's no difference between the men. So this is telling us something really interesting. It's saying that the latent productivity and prominence parameters, once you control for the differences in networks, is not gendered. So this suggests that it's the size and composition of the collaboration networks that are gendered, not the individual capacity to publish hit impact papers or just publish mini papers. We also find that the latent productivities increase steadily. This sort of rise is kind of interesting. People are getting more productive individually. Maybe that's because of computers. Maybe it's because of professionalization of the job, et cetera. Many hypotheses there. The latent prominence over time is flat because of the way we defined it, right? There's only a fixed number of tokens that can appear in the top 8%. And so we're accounting for the fact that number of papers overall is rising over time. So it's sort of reassuring, in fact, that these two lines are flat. Okay, now this is not causal, but it does imply that the effects of known gendered causal factors on productivity, like for instance, the impact of parenthood, may operate as a mechanism by reshaping people's collaboration networks. So for instance, taking parental leave means you are not as present in your social networks, you're not forming those new collaborations, and so that may have an impact on your collaboration networks, which then shows up in the raw data as differences in productivity and prominence. Okay, so that tells us that this one puzzle that's been in the literature for many, many years is just a mirage in some sense. It's not really about the gender of the individuals, it's about how those people construct their collaboration networks. We can ask other questions as well about, say, for instance, early career collaboration. So for instance, how much does an early career collaboration with a senior elite researcher influence you? What's the Mark Newman kind of effect that you might see? So here we're going to define elite senior researchers as those with a high lambda themselves or a high theta. And we're going to look at how those individuals collaborating with an early career person, how that then shapes the early career person's trajectory. So we're going to look at the probability that the junior person becomes themselves an elite author in the same definition by their 15th year, conditioned on them having had one of these early career collaborations. And we're going to look at the probability for the the probability of becoming an elite author having a highly prominent co-author early in your career versus a highly productive one. And what we find is that when we split by, say, non-elite institutions and elite, so MIT would be over here, and where Colorado is. This is a global data set, so what does non-elite mean is a bit weird. Let's imagine that Colorado here is here. but that Mississippi State University is over here in the non-elite set. What you find is that if you have a highly productive collaborator early in your career, it dramatically increases the likelihood that you will then yourself become a highly productive researcher later in your career. And what's interesting about this dichotomy here between elite and non-elite is that you see the same gap, right, between the yes, becoming yourself an elite researcher versus not at the non-elite institutions as you do at the elite institutions. So the effect is independent of prestige, but the absolute value is much higher at the elite institutions.
Sorry, are there two definitions of elite going on here? Elite for person and elite for institution?
Yes, because there's two different things. So elite institutions are the high prestige places. So there's not like a concrete definition for them. It's the MITs, the Ivy League, Stanford, Oxford, Cambridge, ETH Zurich. Like it's that set of universities. Because it's a global data set, I need to go look at the paper to know for sure. The non-elite universities are just a huge class beyond that, right? So the UK, for instance, has 100 different universities, but only like 4 of them are considered elite. And so there's a small number of things over here and a very large number of things over here. The definition of elite of a university is somewhat arbitrary. It's based on reputation, whereas elite for an individual is based on having either a high lambda or a high theta. And this is like in the top 15% of those distributions. Okay, so the point I want to make here is that having the highly productive early collaborator in your career boosts you no matter where you are, but we see more of the effect at the elite institutions, which suggests that there are just more highly productive senior collaborators to be had there at the elite institutions. So this tells us something about like why is it that MIT is such a special place? It's because of the density of highly productive researchers here. That's what makes MIT an elite institution. We see the same thing happen for the prominence, and we see the same difference between non-elite and elite. Again, MIT is a special place because there are the density of highly prominent individuals here. So what distinguishes Colorado from MIT is the people, really. If we look at how this effect varies as a function of the co-author's career age. So I'm going to work with Mark Newman. Let's imagine Mark Newman was not as young as he was when I worked with him, but he was actually like much older, right? So closer to retirement. So what we do is we measure that effect as a function of Mark Newman's career age, and we find that it goes down. The effect size goes down over time. So if your early career collaborator is close to the end of your career, you benefit less over time, versus if they are closer in age to you. Then they have a longer career to sort of promote your work and their work, and you benefit more from that. So this is interesting because it suggests that there's this sort of intergenerational transfer of wealth. If we think about social networks as being a kind of social capital, then this is telling us that that capital can be transferred from one generation to the next, from advisor to advisee, so long as the advisor is around to continue contributing that social capital to you. All right, so overall, this gives us this nice picture of how we can sort of net out the effects of collaborators. It emphasizes the importance of those networks in our own experience and our own track record. It tells us that if you are given a CV from somebody from MIT and a CV from somebody from Mississippi State University, it's difficult to compare them directly. Even though you can look at the publications and you can look at the citations and so on, you can't really compare them apples to apples because they have different networks. And to the extent that where you get your PhD or where you work can structure what kind of collaboration network you have, comparing to CVs, to track records together, you're really comparing both those networks and the institutional basis that those networks are built from. And so this whole machinery that we built allows us to sort of correct for that effect, right? By netting out the differences in the networks and seeing what the individuals can do themselves. I'm not proposing that hiring committees use our algorithm in order to assess their candidates, but it does highlight the fact that sort of in academia, when we're thinking about the composition of the scientific workforce and what we each can contribute, and we evaluate each other. That's part of what we do as academics, is we evaluate papers and we evaluate candidates and so on and so forth. We have to be conscious of the fact that what we're seeing on the piece of paper is not just that person's work, but also the efforts of others. And if we can even mentally correct for that difference, I think we can probably make some better decisions in the long run. So now I want to take this idea and I want to pivot and talk a little bit about the elite world of physics. This was a fun paper that was just accepted last week, and so hopefully it'll come out later this year. We wanted to ask a question using this tool about how elite women in physics sort of fare. So in physics, elite physicists are this sort of special role. Right? So let me back up. In all of this work, we're looking at this sort of bulk of researchers, 200,000 researchers. And so we've got sort of all manner of physicists embedded in that. And you might imagine that elite physicists sort of don't follow some of these patterns that we're just looking at the average. And so we really want to focus in this analysis on just what happens to the elite physicists. And so we want to try to answer this question of whether or not physics is valuing elite men and women physicists differently. Maybe at that sort of stratospheric level of contribution, you don't see gender differences, that the collaboration networks don't matter as much. So what we're going to do is we're going to take our network model. Oh, I'll define it in a minute. Yeah, that's a third definition of elite. I'm so sorry. Okay, so we're going to use our network model in the same way we did before. We're going to try to net out the co-author effects over the same time period. We're using the same data set, but now just looking at physics. And so this is basically allows us to say, like, okay, so controlling for collaborators, we're going to show that men and women in physics are nearly equally productive and nearly equally prominent, sort of recapitulating the result we saw for the overall population. But what we find is that elite women who are elected to the US National Academy, so that's our definition of elite, is you get elected to the US National Academy, which is a very prestigious honorific group, are much less prominent when they are elected, and they get elected about 4 years later. So let's look at some data here. Here's the latent productivity values. Here's 0 in a person's career showing when they get elected. So before that, you see that for these National Academy members, the men and women look the same before they get elected. And over here, for the prominence, you can see that the men are significantly more prominent than the women are. Right? So there's the prominence gap here, but no productivity gap here. So at that line, these two things are true. So women are less prominent than men, but they also get elected 4 years later than men. So men are younger than the women are who get elected. So now we want to ask what happens after the election, right? So if physics is valuing these elite researchers equally, then you would expect to see that these curves stay together and that, well, this is a problem, right? So this is saying that even at the time of election, there's this sort of gap in the prominence of these individuals. But if we look at what happens after, productivity here is sort of the same. This difference is not significant. But look what happens to the women's prominence after they get elected in physics. You see that sort of rises and then becomes equivalent to what the men have. Now, this is all descriptive. It's not causal in any way. But it's very suggestive, right? That the event of being elected to the National Academy changes the probability that women physicists can publish a paper in the top 8% of citations in their field in a given year. And this sort of suggests that it's the way the physics community sort of values or receives that person's work that has changed, not that person. Okay, well, maybe. It could be that the women physicists change the number of collaborators that they work with, or maybe they change the topic that they work on. Maybe after they get elected to the National Academy at the age of 64, they suddenly start working on something that's really sexy and appealing to the mass of physicists. If you know academics, you know that that is a joke. We tend to work on the same things in our entire career, mostly. Like we might move around a little bit. But nobody at the age of 62, when they get elected to the National Academy, is going to like suddenly change everything they do in terms of what their work is. And so that topic shift explanation is just implausible on face value. But if you look at the number of co-authors and their productivity and prominence, that doesn't change at all relative to the election. And so this really suggests that the election seems to sort of correct for this previous undervaluing of elite women physicists. So people who conditioned on eventually being elected to the National Academy, right? There's this gap before election and then it closes after the election. Yeah.
Would we expect that the women post-election, once their prominence is kind of equalized, for their collaborators' prominence to be pulled up as well?
So we're netting out all of those effects, right? In the other people as well. So the productivity and prominence of their co-authors isn't really changing over the election, right? So who they're working with is also not changing. Instead, what we're saying is that the raw probability of them being able to get a high impact paper seems to have gone up. And since everything else is constant, the only possible explanation seems to be that it's how people receive that work, which is the citations. Yeah.
Can you clarify how the high impact is computed? I.e., like, is it like to publish a new paper that later goes on to have top 8% citations, or could it be an older paper that was published previous to their election, but because they were elected, someone's like, wow, what was Aaron Clauset's best paper, and then I go and cite it a ton.
Yeah, so when we calculate the prominence at this point right here, we're looking at papers that were published in this year.
Oh, okay.
So your prominence in this time series is based on the papers published in a given year and then measured a certain number of years later. So we count the citations 5 years after publication and ask, was this paper in the top 8% for that year? So you only have a 5-year window to accumulate that prominence. And so because the prominence is based on time, we're only looking at year by year by year. Yeah. So this effect is not due to people looking at older papers differently. It's looking at new work differently. Okay, so this is nice because it shows us that the effects that we saw in the previous section are not like the tool that allows us to marginalize out the effect of the networks also helps us understand the most productive and the most prominent researchers in a given field as well. It would be interesting to try to take this analysis and apply it to other fields. As one sort of fun note, we did consider other types of elections. So the US National Academies is the most prestigious election. We considered Nobel Prizes, but there's not enough women who have received Nobel Prizes in physics. And there's just not enough people who have received them in general in order to have enough data to make these estimates. We considered the Royal Society. That one is not very prestigious, it turns out, and you don't see these effects for the Royal Society. So in other words, nobody cares if you get elected to the Royal Society as a physicist. Even though it's a nice, prestigious honor, it's not as impactful on your reputation as getting into the US National Academy. Okay. So now I want to pivot and talk about a slightly different type of network. I want to talk about early career network diversity. This is a whole paper that I'm just going to spend 2 slides on. But it has a really nice question and I think a nice takeaway from the analysis. The question we wanted to consider here was, how does the diversity of the early career team that you collaborate with influence the diversity of the team that you might construct later when you're a PI and you are admitting students and training them yourself? And so the idea here is that when you're a PhD student, maybe here, this is your collaboration network that your PI has constructed for you. And that has some sort of diversity to it, say maybe gender diversity or racial diversity. And we want to take the people who go on to have academic careers and ask, how does the diversity here correlate with the diversity that you then construct when you're the PI and you're constructing the diversity of your group? And it's possible that homophily is the name of the game, that if you have an early career experience, if you're a woman, then it doesn't matter what your collaboration network is like. Homophily means that when you get a chance to construct your own network, that you'll construct one that is more gender diverse, have more women in this one. And if you're a man, then you'll construct one that is less gender diverse relative to the norms in most fields, and it'll be more men in this. So it may be that it's only the gender of that person that drives the diversity when you get to construct your own network, and that it doesn't matter what that early career experience is like at all. And certainly there's enough literature in the science of science and the sociology in general to suggest that homophily should be a very strong anchor for how people behave in these situations, that people prefer to collaborate with those who are like them in various social attributes. But the alternative explanation is that maybe preferences are socialized, right? So homophily says that it's the gender of this person that determines the composition here. But if preferences are socialized, then it's the diversity of the network here that shapes the diversity of the network here. So it's less dependent on that person's gender. So here we used a very complicated null model that tries to account for the fact that you have a bunch of these sort of complicated effects in the networks. You have the gender diversity of fields is changing over time. So there's more women in science each year over 1950 to today. So that changes dramatically. And so that already is going to bias your results, right? Because the difference between this moment in time and this moment in time, the pool of people that you might choose these individuals from is different than the pool that these individuals would be chosen from. And so you have to account for that effect. And so we have the null model that accounts for that. We have one that accounts for the particular institution that people are building these networks at. So when you construct your own research group, you can only draw collaborators from the pool of people at that institution. And so if MIT is mostly men, then it doesn't matter if you have a preference for women in your group. You can only choose from the people who are in that environment to begin with. And so we account for time, we account for institutional differences, and we account for field differences, right? So sociology, for instance, is about 50% women at the PhD level, whereas physics is like 22% women. So these three different effects we're going to account for in our null model, which is a very elaborate permutation test that allows us to say whether or not, when we measure the diversity at this point, is it higher than we would expect, given the baselines, those three processes, and how does that relate to the diversity that we see here? What we find is that diversity can be socialized. So so this is men and this is women, this is having a high percent of women among the researchers who are your advisees, and this high is based on this null model. So if you are in the 1 z-score positive relative to the expectation, then you're considered high percentage of women among your advisees, that those who had a diverse early career experience are much more likely than we would expect to have gender diversity in their groups. And the same thing is true for women. And what we find is that it's pretty stable over time. So this is nice because it tells us this kind of, I think, really important punchline, which is that homophily is not destiny, that our preferences for who we work with can be socialized to some extent. It really speaks to the power of that training process of getting a PhD that both shapes like what questions you think are interesting and also how you conceive of building that social environment to do research in. So it tells us that there's a way to accelerate the diversification of science, to get more people in the room to do great science that comes from the way we build our collaboration networks. If we make an effort to collaborate more diversely, our students will benefit from that, and that they will then go on to choose more diverse groups of collaborators when they are PIs themselves. Diversity is a learnable preference in science. Okay, let me wrap up. So how important is who you work with? Networks, I hope I've convinced you, are like an unequally distributed form of social capital because they mediate sort of everything we do as scientists. The differences in the collaboration networks can explain this gender difference in productivity that we've seen appear throughout sort of the study of science in the past 60 years, showing that it's really not about the individuals, right? It's not about men and women, it's about their networks. And so the fact that men do publish more and are more prominent implies that that residual effect is just due to who they collaborate with. And there might be a homophily explanation there, for instance. But it does mean that we really should be careful about comparing unadjusted counts. So if you look at the number of papers that one person publishes versus the number of papers that another person publishes, you should be very cautious in how you interpret those differences, because confounding those numbers are a bunch of these other unmeasured effects, including the prominence and productivity of their co-authors. For our early career analysis, we find this nice sort of intergenerational transfer dynamic in which the prominence and productivity of one senior individual can be passed on to some degree to the junior people that they collaborate with. And that effect doesn't depend on institutional prestige. It's just that the junior scholars at the elite places have more access to those kinds of collaborators, the ones that are highly productive or highly prominent. There's probably a bunch of other stuff that we can look at. A question that my group likes to consider is, can we take this knowledge about how the system works and turn it into some sort of intervention? We wrote a whole paper about whether or not early career fellowships, sort of adding an edge to the collaboration network with senior co-authors, might change sort of the career trajectory of individuals. And there's counterfactuals here, so lots of assumptions. But the punchline of this paper is basically that, like, yes, it seems very promising that if you had a program that would sort of enable these kinds of early career fellowships to, like, maybe a student from my lab would come here and work with Dean for 6 months, then they would benefit from that relationship. And so if we want to increase equity in science, for instance, this is one very natural mechanism to do it, which is just to encourage more people to work together, but do it between groups so that the benefits flow in a desired direction. I'm going to skip over this sort of larger stuff and then say, there's a bunch of papers I talked about here, and then my co-authors. So the papers that I talked about mainly, so Wei-Ha Li was the lead author on several of them. This is some other work from the group about faculty hiring, productivity and prominence in terms of where you work, how labor advantages drive greater productivity of faculty at places like MIT. And then this is the paper that was most of the talk. And thank you very much for your attention.
Cool. We have a little bit of time for questions, and we'll try to use the mic just because this is being recorded, and I know people like watching this online. I thought I'd just ask one to start with, which was about the advisor age. So in some ways, it contrasted with some of the results that I think I recall around how collaborators may end up getting sort of spillover benefits in terms of prominence when somebody's retiring or dying. And so you might.
This was the Science Advances One Funeral at a Time paper?
Well, I mean, I know this literature less well, but
Yeah,
yes,
okay.
I'm thinking maybe of that. I think my colleague Pierre Azoulay has a paper about this, and so you might have thought that like actually early career researchers working with very prominent late career researchers would, in the future, that they would have some structural hole or some other hole in the field that they would be more situated to occupy. And so this was perhaps a little surprising in that regard.
Yeah, that's a great question. So the paper that I mentioned, written by some economists, the title is something like, "Does Science Advance One Funeral at a Time?" Because it's a play on this quip from some prominent, Max Planck, who argued that science advances one funeral at a time, referring to the fact that like if you are a very prominent individual, you have a lot of influence over the field that you work in. And if you don't like a particular idea, then people kind of know that like, like he's the editor of that journal, and so it's not going to get in there or whatever, right? So like these social kinds of effects have an influence on what people work on and how a field progresses. So this economics paper, it was an incredible study design. They went through newspaper obituaries and found reports of untimely deaths, not people who were at the sunset of their life, but people who died in accidents and of cancer and stuff like that, who were prominent researchers in their field, right? And so this gives you this treatment case of unexpected holes in the community, structural holes in the community. And what they found is that after one of these structural holes emerges, the field changes quite a bit. There's an inflow of outside people, there's a burst of innovation on other ideas that are unrelated to what that person worked on, et cetera. And so that paper suggests to me that the expectation that having a very prominent senior collaborator, when they retire, would create a structural hole for it to be filled is maybe too simplistic. That maybe what really happens is that very prominent person who retires and then doesn't publish anymore, that hole isn't filled by their advisee, but rather is filled by other people. That would sort of dovetail with this effect that the more senior your prominent co-author is in your career as an early researcher, the less of an effect you get. Because the structural hole may open up, but you don't get to fill it.
Hi, thank you very much. Maybe I missed it, but do you think there is any issue about the people that actually continue in being researcher? Talking about the next generation, so could be any type of kind of selection that those that continue their career with after graduating from elite schools are those that are like the top on the top, or some people decide not, so you don't see them, right?
Yeah, so selection effects are present in every analysis in the science of science because the fraction of people who get a PhD who then go on to have long research careers, like the ones we studied in this one, right? They have to have 15 years of publishing history. That is not a lot of people. And those who have shorter publication histories drop out for various reasons. Some they choose to go use their skills in industry and government or whatever. For whatever reason, they're not publishing for very long. And so those selection effects are certainly going to change who we're looking at. Here, we're mostly talking about faculty, right? So if you have a publication history of 15 years or more, you must be in a research job, which is pretty stable. In the US, that's typically permanent researchers like faculty. And so you can imagine that like we're just talking about professors in tenure track research jobs at R1 universities here. And that group is relatively stable. The turnover is like 4%. The risk of leaving your job as a professor is about 4% per year. And so most people have very long careers in academia. There are some interesting dynamics. We wrote a whole paper about attrition in academia. And like you would expect, like the attrition rates are higher in the early career and then they go down as you become more established and so on. So how that's changing what work gets done and the degree to which you might have early collaborators that you can pass on your generational wealth to. There's lots of interesting questions there. But generally speaking, we're just talking about faculty here.
Cool. I think we're at 5 minutes till, so there'll be opportunities to ask Aaron some more questions in the reception after the talk. Let's thank Aaron again.
Thank you.